Section 1.4 and 1.5 deals with solving quadratic equations and dealing with imaginary numbers. First one, I asked you to solve by completing the square. This is one of the several methods we can use in solving quadratic equations. To do this, I'm first going to isolate all of my variables to one side and have my constants isolated to the other. Then in completing the square, I take half of the linear term, which is the x term, which is 4, and then square that to get 16. Whatever I do to one side, I must also do to the other so that this equation stays balanced. My left-hand side will now factor to x plus 4 squared equals to 2. To solve this out the rest of the way, I'm going to take the square root of each side. Whenever I take the square root and a variable is involved, I should account for both the positive and negative solutions, so that this whole equation boils down to x plus 4, the square root and the square cancel each other out, they're inverse operations, equals positive and negative the square root of 2. Solving for x, I get x is negative 4 plus or minus the square root of 2. That represents both of my solutions to this quadratic equation. This method is actually slightly faster than just using quadratic formula. It also reduces the possibility that you make an error in simplifying that formula. The next one is a slightly easier method for solving square roots. If I have a perfect square already isolated, I can just take square roots right from the beginning. So I have 9x squared equals 36. Here again, I will take my square roots. And a variable is again involved, so I will have both a positive and negative solution. When I take those square roots, I end up with 3x equals plus or minus 6. And when I solve for x, I get, dividing both sides by 3, plus or minus 2. Second equation, I'm going to solve by factoring. If you notice, these are both perfect square terms. This is 2x to the square root. This is 3. If I want to check if this meets the perfect square condition, I'm going to multiply these two terms together. 2x times 3 equals 6x. And then double that, I get 12x. If your result after that process is equal to this, you do have a perfect square form. And I can take my sign right here. That's my factored form. Had you not noticed that it was a perfect square form, you could have done this by AC method, but it would have been much longer. If you recognize the forms, it speeds up your problem solving process. From here, I will take square roots of both sides. Again, counting for plus or minus, but both positive and negative 0 have the same sign. So I end up with 2x plus 3 equals 0. So x equals negative 3x. For that quadratic equation, I ended up with exactly one solution. Using the discriminant to determine the number and nature of the roots. The number of the roots refers to how many solutions this equation is going to have. The nature of the roots refers to the fact, are they real or imaginary? To figure that out, I will find the discriminant, the formula for which is b squared minus 4ac. The discriminant for this equation, I first have to get it into standard form. To do that, I'll bring all my variables to one side, end up with 2x squared minus x minus 1 equals 0. My a is 2, my b is negative 1, and my c also. I plug all this in, negative 1 squared minus 4 times a times c. My discriminant turns out to be 1 plus 8, which is 9. This is bigger than 0, so I will have 2 real solutions. Find the quadratic equation with integral coefficients that has 5 and negative 6 as its roots. Well, if those are the roots, that means that x equals 5 and x equals negative 6 are solutions to this quadratic equation. Well, that must mean that x minus 5 is a factor and x plus 6 is a factor. So if I multiply these two terms together, I end up with x squared plus x minus 30 equals 0 as my quadratic equation. Again, all I was doing is FOILing these two terms out. Finally, simplifying each of these. I cannot have i's in denominators of fractions, so I will have to multiply this by its conjugate, 1 plus 2i over 1 plus 2i. When I do that, my numerator becomes 6 minus 5i minus 14i squared over 1 minus 4i squared. When I simplify this all out, I get 20 minus 5i over 5. Remember that since I squared equals negative 1, I can replace my I squared values with negative 1 all throughout here. And then finally, I have a common factor of 5, so I end up with 4 minus I as my final answer. For B, if I go ahead and simplify this before I FOIL to 3 plus I rad 3 times 5 minus 2i rad 3. This makes my simplification a little bit easier. Again, since I have the square root of negative 3, this is the square root of 3 times negative 1, which is the square root of 3 times the square root of negative 1, which equals I square root of 3. That's where my term is coming from. I'm repeating the similar process with 2i rad 3, taking out the perfect square of 4. When I FOIL this out, I end up with 15 minus I rad 3 minus 2i squared rad 3 squared, which is 3. Again, I'm going to replace my I squared value with negative 1. So this whole term becomes positive 6. So I end up with 21 minus I rad 3. For part C, I have negative the square root of negative 15 times the square root of negative 5. Well, this is the same as the square root of negative 15 times negative 5, which is negative the square root of positive 15 times positive 5, which is negative the square root of 3 times 5 squared, which would be negative 5. That's it. Hopefully this was helpful for you.